Great. So first of all, thank you very much. I would like to thank Alexei and Yuri and Thomas for introducing my talk. Thank you. Okay, all right. It's okay. Thomas already introduced the topic nicely, so I would like to thank my collaborators. I've divided them into theory collaborators and experimental, and these are various funding agencies. So like Will, I also have a slide which motivates this field of ultrafast dynamics. And yes, I don't need to show it to these audience, but for me, it's really, this was quite important because as you can see, the speed of the processors is saturating. Even parallel computing is saturating now. We can't do more. We can't cram things into smaller and smaller length scales. Now, what we need, and we really need it because Elon Musk is trying to take us to Mars. We have Siri, we have Alexa, our computer needs are just growing fast. So we need to do something about it. And hence we need to move maybe away from charge-based electronics to spin-based electronics. And this was a demonstration. The first experiment, we said that yes, you can. Namely, you can manipulate spins with light. Maybe not in a controlled way entirely yet, but you can do it. And this is very good because then it's more efficient because you don't need to move an electron from one side to another. It's just moving spins and they cause a spin current. It's very fast. But as soon as these experiments came, very quickly a question came, why can you manipulate spins with light? And the reason for that is this. This is the QED Hamiltonian expanding just the first. Thanks. Okay. The Hamiltonian was very difficult, yeah? So this is the QED Hamiltonian, only the first few terms of the Hamiltonian. And as you can see, to the first order, there is no leading order coupling of the electric vector of light to spins. The first time light talks to spins is via this blue term, which is the spin orbit coupling term. Okay, so the coupling is indirect. So we need to now treat our light matter interaction, including this indirect coupling, and let's first see how we can do that. So the theory that I will use is completely ab initio. The only parameter or only thing we will take as an input from experiments would be what laser pulse we use. We use exactly the same laser pulse. And the theory is called time-dependent density functional theory. It's a time-dependent extension of DFT. For DFT, we all know, so we have a many-body system, 10 to the power 23 electrons. We obviously can't treat them. There's still something. Okay. Okay. So since we can't treat these electrons, we treat them as non-interacting particles where all the effects of interactions come in through effective potential. This potential is very, very complicated, but it allows us to treat our electrons as non-interacting particles. And this is the essence of density functional theory. And for this, Walter Kohn got his Nobel Prize. This is the time-dependent extension of it. Here we treat this blue term, here is the vector potential of our laser light. And this is the spin orbit coupling term. These are the effective potentials. In principle, mathematically, they exist. They exist and we can treat our many-body system in this way. And at the end of it, what we get is not the wave function. What we get correctly or exactly like a many-body system is the density and the magnetization density. In this case, we are interested in the magnetization density. So we have it exactly. This is in principle. In practice, we don't know what these functionals are. So we approximate them. And in all my work, I've approximated with LDA. Ask me more details if you want to. Okay, we use this theory. We take a As a test, we take a nickel, big cell of nickel, we whack it with laser, the A field of laser is shown here, and we see what happens. And what we notice is that, of course, nickel demagnetizes exactly as in experiments. And there are two distinct spin excitations possible here. One is what is known as toner excitation, where the spins just flip. And second is that the spins just misalign with respect to each other. A non-collinearity develops. So locally, there's a lot of moment, but globally, the moment is lost, or a combination of two. To test this idea, we look at a big cell of nickel and we see that the moment is going down in the Z direction, but it does not build up in the XY direction, not in the first 100, 120 femtoseconds. This means that's really this first kind of excitation, the flipping of the spins. But theoretically, we can do more. We can divide our subspace into the electrons which got excited and those electrons which were left behind, because light can't excite everything. There are some electrons which got excited, others were just not excited to delocalized states. And we plot the moment of these. The excited electrons don't really do much to the moment. It is the localized electrons where the spins flip. It sounded as a big surprise to us initially, but it shouldn't have. On hindsight, look at the spin-orbit coupling term. There is this gradient of the potential. You excite some electrons, remaining electrons get even more localized, gradient increases, and they feel strongly the effect of spin orbit, and this causes the spin flips. Okay. In all this treatment, we never took care of the nuclei in the sense that the nuclei were always stationary. Okay, they were providing the background potential. However, they were not moving, they were static. However, we need to treat nuclear degrees of freedom if we want to go beyond 100, 120 femtosecond, depending on the material. There are two ways to treat nuclei. One is if you treat them as quantum mechanical particles. In that case, you will be able to treat transient superconductivity, for example. For the present case, it's also maybe sufficient to treat them as classical particles and then do an Ehrenfest dynamics. So I will show you first an example of this. How can we do this theoretically? Remember, we have this effective potential. And if the nuclei are moving, we can change this effective potential to this, where this is the displacement of the nuclei. Now, Hellman-Feynman theorem tells us how much is the force acting. If we know the force and we know the frequency of the mode, we can calculate this displacement, and hence we have this equation, which we can put it here, and we can now do a coupled spin nuclear charge dynamics, all within ab-initio GdFe framework. Let me show you what happens. And what I'm proposing here is a femto-magnetism. So this is iron platinum. We picked this system because I read a few papers which said there is a very strong coupling of the spins to the lattice. No other reason. And here is the phonon spectra of iron platinum. And these colorful things are, the width is how strongly is that mode coupling to the spins. So to the electrons. So this is the electron-phonon coupling plotted here. If you just look at it, you would say, ah, this yellow-orange color, this is fantastic. The mode couples very strongly at the X point. It will do something to the spins. So let's try it. So what I have done now, I've excited the particular phonon mode. And under these conditions, come in with a pump pulse and see what happens to the system. It's the moment of iron and platinum plotted. Iron is reddish colors and platinum is greenish colors here. You see this orange. So the moment is plotted both with and without phonons. With phonons and without phonons is both here. You see this was the orange colored mode. There is no effect almost. And this was the strong coupling, strong electron nuclear coupling. Nothing happens with this mode. However, if you go to the IR active mode at the gamma point, you see a strong effect of nuclear motion on the spin dynamics. Okay, this looks innocent. It's also good news because IR active modes are experimentally possible to excite. So you can think that with your terahertz pulse, low fluence terahertz pulse, you come in, excite a phononic system, come in with a normal optical pump pulse and look at the dynamics. And you see a strong difference. Looks very nice, but let me also give you a bad news here. The bad news is this. These phonon modes have very small amplitude. The amplitude here is 1.2 picometer. Very, very small. So in terms of if you are used to looking at unit cells, it's 10 to the power minus 3 in terms of displacement. Which means if I calculated the exchange parameters or if I calculated the change in the moment by maximum displacement of the nuclei, it's of the order of 10 to the power minus 3 Bohr magneton, almost nothing. This just tells us that the coupling of the phonons to the spin system is highly non-adiabatic. And this, in a way, theoretically, is a bit of a bad news because you have to do all this hard work to see it. You can't pre-guess it. Second bad news, if we looked at the spectrum, if we looked at this, we would have thought that this is the mode which is most strongly coupled. But this is again not the case. That mode didn't do anything. Even if I excited a bigger magnitude phonon, it doesn't do anything. So these are two bad news, but good news is we can do it and IR active modes couple very strongly to the lattice. Now one might ask, what is going on here? Let's just, why does nuclei do that? So let's just divide our time scales into very early times when everything behaves in the same way. Platinum increases, iron decreases, and the later times when nuclei really do something. Okay, now at the cost of sounding like Tolkien, I will say that this early part is controlled by what is known as OISTR, and I will explain OISTR to you. The best way to look at OISTR is in antiferromagnets. Let me tell you what OISTR is. I show it to you in this ferrimagnetic case. You have a few layers of cobalt, 2 layers of manganese grown on top. Manganese tend to couple antiferromagnetically or in a non-collinear way, and that's what you see. This is the magnetization density plotted. One manganese atom up, one down, and everything else is pointing up. So it's a ferrimagnetic system. You come in with a pump pulse, you pump the system, and you see what happens, and you see that one of the manganese, so this yellow and red are the two manganese atoms, blues are cobalt. One manganese atom loses its moment, turns, goes to the other direction, and transiently you see a ferromagnetic-like behavior. So you have switched to a ferromagnetic coupling. And then one asks, okay, in the first few slides, I motivated this talk and said, hey, spin-orbit coupling is everything, right? Then you do a calculation with and without spin-orbit coupling. There is no difference. This one is reddish, two manganese atoms, one is shown in reddish color, other in this bluish color. There is no difference. You see this switching happening despite switching off the spin-orbit coupling. So spin-orbit coupling is not the reason here. The reason here is OISTR, which is optical intersite spin transfer. And the reason behind it is purely availability of states. Namely, nature does what it can. So these are the two manganese atoms. They're antiferromagnetically coupled. Imagine you come in with a laser light on this red blob of electrons. They have no place to get excited almost. There are no states available on its own site. So a small current flows and it goes to the neighboring manganese site. Remember, optical excitations preserve spin. So up spin has to stay up and down has to stay down. So this little current flows and goes to the nearest neighbor manganese. And in this case, here, the two currents flow of the opposite spin next to each other. Eventually, because the moments are not exactly the same, one is -2, one is higher, one of them turns. Okay, this is the phenomenon of optical intersite spin transfer. And this is what happens in the first 20 femtoseconds. After we proposed this OISTR in 2018, there have been several experiments. These are all experimental works which show that, yes, it really does exist. Now comes the interesting part of phonon and magnetism coupled, namely afterwards. What happens here? What is causing all this to happen? So let's just plot the difference between having a phonon and not having a phonon. Just plot the charge as a function of time. What you notice is that rattling of these nuclei, they cause a current to flow, a charge current to flow. And this is an IR active mode, remember? So the minority and the majority current flows. Minority spin current flows from iron to platinum, which means platinum demagnetizes because it's getting minority charge into its subbands. And because iron loses minority, it has lot of minority states empty, and now the spins can flip. And that's what happened, and that causes iron also to lose a lot of moment. Okay, so we find out here what the reason was. You can find more details here. Now, is this based? Is this, I showed you a case of ferromagnet and that to iron platinum. Can we say something more about it? Especially about switching? Then we try iron gadolinium. And we again excite the IR active mode. And we look at the moment of gadolinium and the moment of iron. And you can see how strongly the moment of gadolinium depends. It really couples strongly to this mode, which means you can speed up the switching. Now, I have not prepared an extra slide for this, but you have to believe my word for it. This is the moment plotted in the Z direction. In iron platinum, I showed you how this current causes the increase of spin flips, not in iron gadolinium. In iron gadolinium, this coupling to the nuclear system causes the moments to cant away from their easy axis. This canting is needed in iron gadolinium to cause the switching. Okay. So this is a penultimate slide where I want to show you a teaser. Up till now, everything that I showed you was all to do with magnetic systems. You come into a magnetic system, you first excite a phonon mode, then you come and pump it and do things like this, play around with laser pulses. Here we talk about Hall effect. These materials are not magnetic, so it's in the work here, you can see all 3D, 4D, and 5D metals studied. Everything is presented here. Here I just pick a few nice examples. What we say is usually when you look at the spin Hall effect, you look at the zero frequency limit, you look at the long time limit. This is the optical, so to say, spin Hall effect, namely you pump it and you look at it at finite frequencies. This is just the ratio of the spin current to the charge current. And you can see that actually the spin Hall effect is much larger away from this zero frequency limit for almost all the metals. In fact, if you resonated your pulse with X-rays, it's even more than 1, namely the spin current is huge. Okay, so this is a teaser, and please ask me something about it later on if you like. We can discuss more because I'm not an expert on Hall effect. Okay, so what is missing in the theory? A lot, frankly. And here is a diagram of what is missing and what we are actually right now working on. There are publications related to all these topics, and I won't present them, but I will tell you where we are pushing the field towards. I showed you the spin orbit coupling term, but I also showed you the QED Hamiltonian. It has lots of terms, and some of those terms are very important for spin dynamics. One classic term being dipole-dipole interaction, where there's domains, domain walls, all these things are, and their dynamics is influenced. We have now found a way to include this, and because we are doing density functional theory, we can't just include it. We need to include it by functionalization. So this we have already done. We have functionalized the dipole-dipole interaction, and now we would like to study long large objects like skyrmions and domains and domain balls and their dynamics. What is also missing up till now has been coupling to the Maxwell's equations. For these 3D systems in the present format, we didn't need it. But if you go to two-dimensional systems, you have excitons and you have dynamics of these excitons. And if you insist upon doing it within the realms of time-dependent density functional theory, there is only one way to do it, and that is to couple to the Maxwell's equations. There is also a gauge fixing needed. I didn't give a talk about that, but that also gets fixed because of the Maxwell's equation. So this is our next task. We are going to couple to the Maxwell's equation. What more we need to do is that right now we are studying 10, 20 atoms in a unit cell, roughly, and no more. Not sufficient. We want to study dynamics of skyrmions or larger objects which are nanometer sized. This is a problem which has been within the field of ab-initio physics, that you can't do such huge systems. We are talking millions of atoms here. And in order to overcome this, we have now extended our methods. We have proposed a new method, which is called ultra long range. You stay within the unit cell, yet you are able to treat very long range physics. This work is already published, but we need to now combine it with GdFe, namely make it dynamical. The nuclear degrees of freedom I showed you right now, but they are still classical. We want to make them quantum mechanical, which we have formally done, but it needs to be made transient. And we need to do a full molecular dynamics. When we have done all that, this is what we are going towards. Then we have this very long range physics. We have coupled to Maxwell's equation and we have done dynamics. We will have light propagation, density wave propagation, light. So we go towards photonics, light talking within the material. If you have long range, you have spin orbit in spin density functional theory, then you can treat the dynamics of skyrmions. This is what we are at the moment working. If you have long range, you have dipole-dipole interaction, you have time-dependent spin DFT, then you can study magnetic domains and their movement. If you have quantum nuclei, you have long range and you have superconductivity included, superconducting order parameter included, then you can study TD superconductivity. And this is one of the aims we are pursuing, namely creating an excited superconducting state of a material with laser light. So we can find a lot of new physics at competition, just by competition of energy scales. All these things are being implemented and done in this code called ELK, which stands for electrons in K-space. And it is a GPL code. It's released under GPL license. Everybody can use it and download it. And I'm very happy to say that out of 500,000 projects, it has won the community award this year. So to summarize, I showed you that the early time demagnetization in elemental magnets is controlled by spin orbit coupling. However, when you go to multi-component magnets, all the early time physics is controlled by OISTR. And we have now got a way to couple to nuclear degrees of freedom, which offers us even more control over these magnetization. I also showed you some large spin Hall angles as a teaser. And now this is the new proposal that you can do femtosecond phonomagnetism by cleverly coupling the 2 degrees of freedom. Thank you very much.